Some problems will only give initial concentrations of the reactants or products and no equilibrium concentrations at all. These types of problems are a little different because instead of solving for K, we're given K and we're being asked to solve for the equilibrium concentrations. To do this, we'll use an unknown variable X in the change row. The example says we started with 2 moles per liter of C. Since A and B are not mentioned in the problem, we'll assume they aren't present at the beginning of the reaction and fill in the initial concentrations of 0 for both. If reactant A increases some unknown amount, X, then B will also increase by that same amount, because there's a 1-to-1 ratio of A to B according to the balanced equation. And if A increases by X, that means C will decrease by 2X, because there's a 1-to-2 ratio of A to C. So the change row still follows the stoichiometry of the reaction, just like before. Fill in the equilibrium concentrations of X, X, and 2 minus 2X. Our goal now is to figure out the value for X, which we can do by plugging in our unknown concentrations to the equilibrium expression with our given K. Now don't forget to plug in X to your equilibrium concentrations. Your final answer is 0.5 molar, 0.5 molar, and 1 molar for your reactants and product. Percent dissociation is another type of icebox problem that we'll see. In the example, we're given 2 moles per liter for the initial amount of SO3. And since SO2 and O2 aren't mentioned, we'll assume they aren't present at the beginning of the reaction and fill in initial concentrations of 0. Now the problem says that SO3 dissociates by 5%. So instead of being given the exact change, we'll calculate the change, which is just 5% of the initial concentration. The change row follows the stoichiometry of the reaction. So if SO3 decreases by 0.1, SO2 will increase by that same amount, and O2 will increase by half that amount. Now we can calculate the equilibrium concentrations, and then plug in our equilibrium concentrations to solve for K.